Yeah, no worries. But when Sitarama had requested me to create a presentation, I gave him the topic, and his reaction was, "Hey, I like the topic, but I worry that it might need a 45-minute to an hour, and we don't have that kind of time." And I told him, I don't have that kind of expertise in Wi-Fi to speak for that much, so I'll keep it succinct. Let's see if I can do a decent job at it. So one of the things, while the slides come up, one of the things that I wanted to actually see if we can achieve today is be honest with ourselves as Wi-Fi industry in critiquing ourselves, as well as giving us ourselves a pat on the back, in what we have done well. Right, I've been in the Wi-Fi industry for 15 years now, and there are others who have been there a lot longer. So this is the topic I wanted to have. Moore's Law met Wi-Fi, and Wi-Fi won't shut up about it. What did, the transistors that we added into the Wi-Fi chips achieve for us, achieve for the consumers, right? That's sort of what I wanted to get to. Some things have gone well, others haven't. We are here now, and in the raw compute power has increased, but some of the problems that existed in 2005 still continue to exist. Microwave runs, you have interference problems. We still haven't gotten past some of these more fundamental problems, interoperability and the likes, that continue to haunt us. So, what did all of these years of Wi-Fi innovation do? Okay. So since I talked about transistors, what is it that we have done? Originally when we started with 11B, it was just a baseband chip. But over time, it has accumulated transistors and capabilities. When 11B to the G transition happened, it got a little better. Then there was more processing happening. More was starting to happen on the host processor, and so SOCs came about. So when the SOCs came about, I think there was still a question of how is this going to be leverageable. 11AC Wave 2 did a fantastic job of leveraging it. I think Qualcomm's Dakota chip, was, I think, by far the largest selling Wi-Fi chip at some point. And so over time, things started accumulating. Then came the IP accelerators. With the IP accelerator embedded, things started happening faster. Now, then we said, okay, what do we do with more capacity? What can we do more to innovate? And the answer was, oh, we'll add NPUs and security engines. Okay, so if you look at this transition, just in terms of scale, don't worry about the numbers. Just look at it for scale. It's sort of like from what was minuscule to maybe 50 times more in terms of, and probably more. I suspect it's more like 200 order of magnitude, larger in terms of the number of transistors. So what did it achieve? So what are the good stuff that happened? I think SU MIMO and beamforming were two things that, I think really did make a difference to the user experience. So there was a lot of parallel DSP that was needed. And so the real silicon, the real gains in SNR, all of that happened. So it was definitely worth the transistors that we put into it. OFDMA, a little bit controversial. I know Susinder is here and he has strong opinions about it. Susinder and Rasika were kind enough to visit our office at Netgear yesterday. Thank you, guys. And so we had part of the conversation around OFDMA as well. When it works, when it is actually used, it has benefits. But is it usable all the time? The answer is no. But at least where in scenarios where it was able to give benefits, it did. So when 11AX came about and OFDMA came, I think it added a certain level of value to that end. MU MIMO, this is the one that has eluded us for a long time. MU MIMO, basically, the physics of it is solid, it works. but you just cannot have the kind of spatial separation, the antenna separation needed in these access points. And a 4x4 antenna rarely has enough spatial degrees of freedom to be able to achieve this. Probably when we get to maybe a 16 by 16, we might start seeing the impact of MU-MIMO. Whether it'll be useful or not at that point, I don't know. But that's when MU-MIMO actually can make a difference. The security accelerators were real. When cryptography, needed latency to be solved, security accelerators did that job. And with that, you actually got real line rate performance with security to be good. So those are the things that happened well where transistors made a difference. So I wanted to think for myself, take a step back and see, you know, in all these years of being in the Wi-Fi industry, what has gone well, what could have gone better. So sort of a report card for ourselves as Wi-Fi, some experts and some novices. So 11B brought Wi-Fi to all of us. I think I wasn't very sure about Wi-Fi at that time, but the only thing I knew was, hey, if Apple wanted to experiment with something, there must be something to it. So when the iBook, came with Wi-Fi embedded in it, I actually bought that thing to say, okay, let me see what, is this real or not? Still questionable, but I think the fact that it was able to make that entry point and impact is what gives it a in grade. Then comes 11G. 11G actually, the timing of it was fantastic. Broadband started coming in, and so with the 54 Mbps, and backward compatibility to 11B, all of that made this very good. The speed argument made sense. Well, at least in the US at that time. And back in India, I think that I remember DSL was still there, and maybe if I got 246 kbps at home, I would be happy. But with time, things improved. 11N, the first real physics work happened. SU MIMO, beamforming, MIMO diversity, all of these are things that required real DSP and real physics, and that's what the Wi-Fi industry brought as part of the 11N standard. So, and I also can say, many people at that time used to, connect all their rooms with Ethernet wires so that they could have physical connectivity at home in every room. But 11N was the first one that gave confidence that new homes, you don't have to build with Ethernet to every room. So that is real impact, and so I gave that a minus. Why not A? Because while it introduced SU MIMO and beamforming, it didn't do that really well. It did okay, but 11AC perfected those through that transition, right? So 11AC, especially Wave 2, turned out to be the redefining in a moment, in my opinion, for the Wi-Fi industry. And to that end, I give it a A. Mesh, became ubiquitous at that point for home networks. Until then, mesh was talked about. The Wi-Fi standard having 11S for mesh was always there, but it never caught on until somebody like a Eero said, okay, I'm going to play with it and bring this out. And I think 11AC enabled that. So Wi-Fi as infrastructure, I think that really happened with 11AC. And to that end, I'd give it an A. 11AX, in my opinion, was rather disappointing. BSS coloring, TWT were all things that it brought in. But what was the user experience, user impact because of it? Almost no real impact, in my opinion. So, in fact, 11AX, I remember At that time when 11AX was launched, there was really not much traction going for 11AX in the market. People were still going after 11AC Wave 2 chips. And then, thank, thanks to COVID, the Qualcomms and Broadcoms of the world decided, hey, this is a perfect opportunity. There's a lot of demand for Wi-Fi. I'm just going to kill 11AC and say I don't have chips anymore and start shipping 11AX. That's really what took 11AX in mass volume to the market. Not any features that it provided, the impact it provided, or the throughput it promised, or OFDMA, none of it. So to that end, I think AX iffy. Um, okay, now 11BE. Again, one that has more question marks than answers, in my opinion. And I put my. This is not a critique of the chipset vendors or anybody like that. It's I am also part of the industry, and we all have to be honest to ourselves in critiquing ourselves so that we can be better the next time around, right? So to that end, MLO, came. What impact, if any, did it make? Do we even have, at one point, I think even the chipset vendors had MLO turned off by default. And then the OEM started turning it off later once the chipset vendors enabled it. But it still isn't clear what value it is adding. Yes, some people say, okay, mesh backhauling, you can link and all of that, but do you really see the value of that showing up on day to day for a consumer, whether it is at home or enterprise? Any of these that 11BE has brought, have you seen that value show up? And so far, to me, whether as a technologist or as a end user, I would say no. So then the industry also came up with this new terminology. We always need things to, do marketing, right? So AI native was the next keyword that came about. And I think every chipset vendor talked about AI, but what AI meant to the industry, what impact it has so far created, and what can it possibly do? My analysis, again, I don't claim to, claim to be the expert knowing what happens everywhere in the industry, but based on what I have seen, here is how I would grade it, right? To me, when people say neural engine, I think that's been there since the late 90s in DSPs. And so we just rebranded that and called it neural engines. Then comes AI powered beamforming. Okay, that I think this is one. Indirectly I poked Susinder yesterday and asked him about AI, and he said, "Oh, for AI to have impact, it should have nonlinear algebra." But currently, when you talk about beamforming, it's basically SVD based beamforming, and so a lookup table with different environment profiles and all of that is what is happening with AI powered beamforming. But SVD by definition is linear equations. It is not nonlinear. And the other thing that Susinder also mentioned, and I was like, okay, hey, I'm glad at least somebody thinks what I put in the slide is right, even though he didn't see the slide. But basically, you need reinforcement learning coupled with, nonlinear algebra for this to really work. Otherwise, what you will do is, what essentially beamforming does is takes a stab at directionality and says, okay, hey, here it is, and you're stuck there. It is assuming, essentially, basically the channel state information to be perfect. On-device inference engines. This is real. Client classification and interference detection. These are things that you can really achieve, and I strongly believe these add value. SON, self-optimizing networks, band steering, channel selection, you can call it any different name. But again, something that happened in 2014, 2015, rebranded now. So where do I think ML actually earns its transistors? In my opinion, interference classification is something that it can do really well. I think we talked about this partly. My question to Rasika was more leading to this, and so I think inference classification is something it can do really well. CNN on spectrograms, I think, are going to be very worthwhile. Then comes the client capability prediction. So this is where, which MCS do I want to settle on for a given client to sustain the performance, not one that you're constantly keeping on adapting, right? So if your typical rate control algorithms can leverage something like this to do better. Anomaly detection and security. Okay. So this is another area where I think the Wi-Fi industry hasn't evolved at all. Um, you know, IoT devices, fingerprinting has been talked about for a long time, but I don't think it has happened really well. So how can ML detect these and use this for security and anomaly detection? I think this is one where I'm very, very confident that even third-party companies should be able to create algorithms that somebody like a Qualcomm's chip can load it as a third-party software and be able to leverage much of this. The channel quality forecasting is another very important area in my opinion. So this is one that you can use for reducing the retransmissions before it happens, not post retransmissions. How do I adapt and move? So to summarize, what did Moore's law buy? Physics improvements, certainly. MIMO, OFDMA, beamforming, we talked about all of this. So silicon budget was needed for all of it. ML inference engines, we talked about just now. I think those are really valuable. There are scenarios where there are features that required compute power to implement, certain features, and it added value there at a SoC level. But band steering, channel selection, repackaged as AI is not it. And some of the more fundamental problems, IoT, those are not solved yet. So what is it that we can learn from what we did well to do better again in Wi-Fi? How do we reinvent Wi-Fi to be something that's not just a standard that comes out every 4 years and so chips that come out? How do we redefine the user experience of Wi-Fi? That, I think, is the lesson we all need to learn from 11AC, in my opinion. The three things that I believe, if we solve well, can be transformational to the Wi-Fi industry. I keep hearing people talk about Wi-Fi becoming commoditized. But something needs to revive that industry, and I think solving some of these problems well can do that fantastically. Roaming 11K, 11V, 11R, all of this has existed for more than 15 years now, right? So, but is that really working? Cross-vendor implementation, the client, doing its own thing. The beauty of Wi-Fi is it's like it is designed to think like an American parent. You have the child does its thing. You can't really discipline it. You just have to figure out how to, make the child be a good kid without being able to give it a whack, right? So the clients do their thing. The AP adapts to what the client does, and so roaming is still a piece of crap. Latency under load. This, I think, there are multiple levels of latency under load that I think we can talk about. So, um, consumer QoS and scheduling is still, I think, quite crude in what we do. Where the number of devices increase in a household, the latency problems start showing up. But there is also other futuristic use cases where latency, if we can really solve it well, can be dramatically useful. For example, in AV networks. In AV networks, because there is PTP and timing and things like that, the latency requirements are very, very, very rigid. You need to be consistently under 3 milliseconds with a certain expectation on packet loss. Those are things that, if they can be solved well, they can be transformational for Wi-Fi. Then comes the IoT coexistence. So as IoT devices keep increasing, how can they coexist in the homes? How is this problem solved? How do you solve the microwave problem? All of this, I think, if we solve these in parts, we don't have to solve all of it in one shot. If we solve these in parts, basically you're addressing a real user problem, not a science problem. So solve user problems, and I think Wi-Fi will be back at it again. So in summary, Moore's law kept delivering, Wi-Fi spent it well once, and that was in 11AC. After that, we have a lot of transistor budget capacity, all of that, but we haven't solved real problems for the end user. Yes, we're talking about UHR and things like that, but I'll wait for it to solve the problem before I declare victory. But thank you for the opportunity, and I think I finished with 4 seconds to go.
Thanks. So I think you've set the stage for people to be hungry for lunch. So we should take some questions before Vardhan or Sitarama say lunch. So yes, questions for Sudarshan. Please put up your hand and mic will come. Yes, Ponmudi.
Yeah, Sudarshan, one thing is like all our backbones are barely like few BBS, right? The ISPs that we get at home, and whatever you do after that, right? It is not going to do a big magic on that. So that becomes a bottleneck for us right now. So that is one point. And another one is like, so how do you define a better user experience with Wi-Fi? What would be your definition for a good user experience?
I just said those 3 things. Roaming.
Roaming.
In fact, yesterday, when Rasika was at my office, the first question I asked Rasika and Susinder was, if you had to do one thing in Wi-Fi, in enterprise Wi-Fi, if you had to only fix one thing, what would that be? And his answer was roaming. So, it's experts like him that are speaking. I'm just the mouthpiece. So, roaming is a real problem. I haven't seen any vendor. Aruba is here. Can you claim you've solved it well? So, it is a problem that we need to solve and solve well. Until we solve that, people are going to keep complaining about Wi-Fi.
But the AP people will say, as Susinder said, it's the clients which are spoiling the show. So what do you think we should do?
Give it a whack. Be the Indian parent.
Yeah.
One thing I found very much interesting is that getting in A and ML into the rate selection algorithm part. So currently, the rate selection is almost based on the counters that are the counts from the MAC and file layer at that instant. Like fitting in A and ML, won't that increase the latency? How do you see that A and ML can play a...
So that's where I was talking about being predictive, right? So right now it is reactive. So within reactive, if you add AI and ML, I entirely agree with you that it is going to cause problems with latency. But what we need to do is be predictive. That's where AI and ML are going to help in this process.
Okay. So predict the environment and we are going to fix the specific rates for that environment.
For
You're not
each
going to
client,
use it.
for each client, be able to predict what is the MCS that is going to give it the steadiest experience. That's what I mentioned in the slide as well.
Got it. Thanks.
I think one more question. There's a hand up there. Please get a mic.
So using AIML in real clients, how the OFDMA and MU performance is getting improved with using AIML and without using AIML, how the real client is getting the performance.
Like I said, MU MIMO, there is no performance gain seen by any real client. Even to create that experience within the lab, I'm sure every chipset vendor and OEM is doing all kinds of magic just to say, hey, I got this use case working with MU MIMO. Would you agree? So there is really no improvement right now, and it's not a problem of algorithms. It is a problem of physics, right? So the spatial separation needed is just not there. So there is nothing you're going to be able to do to algorithmically solve this magically.
So we cannot go with about 2x2. Currently, we have only 2x2 real clients, right? So there is no probability to increase the from 2 spatial stream to higher due to space constraint.
Unless you get to 16 cross 16, MU MIMO ain't working, not reliably, predictably.
But he's talking about the AP side 16
Yes.
cross 16. So while he was mentioning the client side 2 cross 2, that's okay, right?
Client side 2 cross 2 is okay, but on the AP, you need the spatial separation in order to be able to achieve this. Somebody there?
Somebody last row. Do we have still time for questions? Sitaraman, Vardhan, you have to tell me. Last question.
Hello. Shouldn't we consider Gen Z's client data load? Let's suppose you were thinking in the backward 11 AC. We should also consider VR, AR based use cases which is coming in. And Wi-Fi 8 also should be given a focus. And shouldn't we consider Gen Z's or alpha kids use cases?
Again, I did not say go to 11 AC, for anything other than learning lessons of what happened right.
Right.
So yes, I agree that Gen Z are going to be the biggest consumers going forward, and their problems need to be met. But their problems are still going to be around the same types of things. If you solve roaming well and latency well, your AR, VR, all of those are going to be solved well, correct?
People are not roaming. They are sitting at theaters. They need a higher load.
Yeah, okay. I do agree. I'm the old dude. So, but you do bring up a very valid point. Again, the intent of the thoughts here, and I want all of you to participate as well, is in helping define what are the real user problems to solve, right? When we understand the real user problems to solve and start participating in standards, I'm talking about going to Wi-Fi Alliance and actually representing the user and not your company.
Okay. So thanks, Sudarshan. Sudarshan will be back for the panel, so you can also get more shots.